I'm going to assume that you know the basics of Untitled Studio in this webinar, and if you don't, there's a recording of the Getting Started webinar you could look at later. So I select my project and I start a debug session. I now have enabled tracing in my debug configuration, and this is a prerequisite in order to be able to do this tracing. So let's just show you where this is done. I can go to Configure Debug, and this must be done prior to the debug launch. Here I have, it seems, two different debug configurations, one for each project. This configuration, which is for the STM32F4 discovery board, I can change its settings on various tabs here. What I'm looking for is on the debugger tab, where I see that the ST-link is the selected debugger. And here I need to make sure that this checkbox, Enable Serial Wire Viewer, is checked in order to be able to do tracing with the Serial Wire Viewer. The core clock should be set up automatically for you, and the SWO clock will set the max limit of data you're able to transfer from the target back into your IDE. So with this tracing mechanism, we're using a hardware support which is enabled in Cortex M3, M4 and M7. It is an extension of the serial wire debug interface, which just add one additional pin, which is the serial wire output pin, a pin transferring data back into the debugger. Yeah, so it's available in all these Cortex M3, M4, M7. It's a cheap option and it gets you quite a long way. So you should really try it. So yeah, you need to have that enabled and then start a debug session. But since I'm already in a debug session where I have this enabled, I'll just click close. So serial wire viewer tracing. What do we mean with that, and what is the capabilities that the debugger gains with this? Well, the serial wire viewer is an event-based type of tracing, which means that we can configure the microcontroller core to emit trace data based on certain events that occurs. So what do I mean with events? Well, let's look into the configuration of the trace. I can configure the trace to output trace data on for each program. We can sample a program counter, and each sample generates a trace data packet back into the debugger. And by doing that, we can enable statistical function profiling. Also, we can have the target generate trace packets as soon as an exception or interrupt occurs in the target. So that's another type of event that can generate trace packets. And here is where I control which types of events that will generate trace data. A best practice here is not to enable too many types of events to generate trace data at the same time, because you only have one data pin transferring trace packets back into the debugger, so you will get you will choke this line. It will get overflows if you try to transfer too much. Anyway, there are a couple of different cool use cases that I'm going to show you now with this tracing technology. And the first one is to use the old classic Printf debugging, but instead of hooking up an RS-232 terminal and messing around with adding code for that, instrumenting your application and having these cables consuming I/O pins, etc., I'm going to just use what's called Idm Ports. There are 32 available Idm ports in your CPU core, which can be set to redirect printf traffic back to your debugger through the common debugger interface, the USB cable in this case. from the SD link to the PC. So in this application I have instrumented it to transfer trace messages on port 0 and port 1 by enabling port 0 and 1. So I'll just click OK here. Then I have a view. I, by the way, have many views, but all the views which are prefixed with SWV are related to tracing, serial wire viewer tracing. So you see there are more of those here. First, let's show you the serial wire viewer console. So this is the equivalent of an RS-232 terminal, a serial terminal. I have port 0 and port 1 open to show data coming from there, those ports. And now I need to click Start Trace. This enables the PC side to receive the target information as we receive trace packets from the target. So let's now see here. Here I have a printf statement that will print information to port 0. So if we run the debugger to this line, run to line, and then we step over this line, and hopefully we should get a printed message here. So this is a more convenient way of doing printf style debugging, which gives your application lower timing penalty than using the RS-232 terminal, and it's just less of a hassle. Now this application, let me remove that breakpoint, watchpoint isn't enabled in this project. So if I resume the execution of this application, you will see that this application has been instrumented to output trace messages on port 0. Here we are getting variable values of the accelerometer on this board. So the function that reads the accelerometer values is instrumented to print the values to port 0. On port 1 we have instrumented the FreeRTOS kernel to output task switch events on port 1. So you can instrument different portions of your application to output different types of trace messages on different ports, which is quite convenient. So that's one of the possibilities with the serial wire viewer tracing, to redirect printf statements back into the debugger without having to use UART RS-232 terminal. Another cool feature is using exception tracing. So now we are going to tell the CPU core to emit trace packets as soon as we enter, exit, or return from exception execution. Check that. I'll also check timestamps, and I click Start Trace to record it into the laptop PC buffer. I will open a view I call Serial Wire Viewer Exception Trace Log. All these views I'm showing here, they are available here. Show View, then you have Serial Wire Viewer, and you have a number of different views to help you with different debugging related tasks. So, as you see, the same toolbar here are available here and here. So it's essentially the same operations there. I continue the execution of the application. Oops. And I now see how I receive exception entries, exits and returns while the application is executing. So let's pause the application again to see what it is that we actually get here from the target. Here we see that we had an exception entry of the SysTick peripheral. It's part of the CPU core. It's implemented in the SysTick handler function, and we got this on the CPU cycle corresponding to this value, and the timestamp was this. I can double click and I will be taken to the SysTick handler. So since this is a FreeRTOS application, there's probably a macro expanding SysTick handler to this function. Here I have an exception exit. So comparing these two timestamps gives me the information of how much time I spent in the SysTick handler. And here I go back to normal user code execution. Sorry, no I don't. Here I do that. So it seems that the SysTick happened, and then while the SysTick was executing, we entered the pending service routine, which had a lower priority, therefore it did not preempt the SysTick. So what I want to say is that here we get a time chronological information on how our exceptions and interrupts fire in our application. We can also turn this data around to get statistical information about how our interrupts and exceptions are performing in this application. So there's a tab called Statistics here. If I move over here, I can see the exceptions and or interrupts that has occurred. This application only uses pending service routine and SysTick, so no timers, no analog digital conversions or whatever, therefore not showing any of those. The handler function, here I see the number of exceptions of each, and this then is the corresponding percentage. So even though it seems we have a quite even number of exceptions, 11,000 of the pending service routine and 10,000 of the SysTick, we can see that out of the time spent executing exceptions, the pending service routine consumes almost 94% of that execution time. So that could be interesting profiling information for us to understand how we should optimize our exception and interrupt handlers in order to obtain a better performance in the application. The data here is shown in different representations, and we get the average runtime, we get the fastest and the slowest, etc. There's a lot of data here that can be analyzed and which you can then base your optimizations on. So this is also another opportunity you have with the serial wire viewer tracing on the Cortex M3, M4 and the M7. Next feature I want to show you is to do, let's call it global statistical profiling of your application. So now we were focusing on exception and interrupt handlers to see how they were performing. Let's now take a look at how the application as a whole is performing by having this trace module send the PC samples, program counter samples, as we are executing the application. I can set up a resolution, sample rate. Let's stick to that, and then I click OK. Then here I have a view, let me close that, called Serial Wire Viewer Statistical Profiling. I click again Start Trace, and you see it enables in all the other views at the same time. Same button. And then I click Resume. So now I am running my application in my embedded target. I don't get any feedback here because there, well, it seems I do get a little bit, but what I'm doing now is collecting program counter samples, and as soon as I pause or suspend the execution, we will post-process the collected program counter samples to display where we spend the most of our execution time in our application. So there seems to be one function called toggle state, where we spend almost 40% of the execution time. So that gives us a good idea of where we perhaps could do some optimizations if we are having a small system with really limited resources. So by double-clicking here, I'm taken directly to the code where the functions are implemented so that I can fix things, look at code, etc. What you see here is, here you see the information of how many samples we collected. So almost 54,000 program counter samples. And here is how they are divided amongst the functions. So almost 22,000 samples within this function. So that means between this start address and this size, so to speak, which is the size of the function. And that's how that can be calculated. Yeah, that gives you an idea of where you should perhaps refactoring your code, where you should perhaps put some function into a faster accessed memory, or other ideas. So that was the statistical profiling. A last thing I'd like to show you related to serial wire viewer tracing is the data tracing. There's what's called the DWT, the Data Watch Trace Unit something, which has 4 hardware comparators that can be set to monitor up to 4 different memory addresses in your embedded target. So here I have simply written some variable names, some C symbols, which the debugger automatically converts to the hexadecimal memory addresses. So I can write the symbolic name or hexadecimal address. Then I can also decide which type of event that should generate a trace packet, a read or a write or both. So if I now read from or write to this variable, I will get a trace packet sent back to the debugger showing, what am I showing? That depends on what I select here. I can select to generate the program counter value, which gives me the information of which code line that, that made the access to this variable, or see the data value as the read or write happened, or both. So I'll just choose data value there. So I have now set up the trace unit here, these 3 hardware comparators, to watch 3 different variables that are associated to the accelerometer on this board. I also enable timestamps, because if I have timestamps, I can plot the data values against time. So let's start the trace again. I'll just clean the serial wire viewer data buffer here. Not necessary, but let's do that. So I'm going to show you 2 different views here. One called serial wire viewer data trace. It will show you a log view. And one called serial wire viewer data trace timeline. That shows the same information in a graphical representation. I'll click resume. And now I'm holding the board still, or relatively still it seems. Now I'm going to start tilting it. And you can see that the accelerometer, I'm tilting it in one direction, and now I'm tilting it in another direction. Or just generally shaking it. So, as the accelerometer is writing to these variables, we are tracing these accesses to this data structure. Here, you see what's going on here in the graph. The same information is available here. So here I see comparator 0 is associated to the variable name axle x-axis. It has the current value 1. And let's toggle scroll lock so that I can scroll in the history here. And here are the historical values that we have collected. Write, read, cycle count, etc. For this comparator, I did not enable program counter collection but I think I did that for this comparator. So when I select number 1 associated to the y-axis, I also get data in this column, the program counter column. Let's rehearse and see what happened. That is because for axle y-axis, which is on comparator 1, I have generate both data value and PC. So data value and PC. So let's now play with the thought that if I get a minus value, it means that we have a bug, and see how this can be used to find bugs. So somewhere here we received our first negative value. If I now double click here, I can jump to the code line using this program counter information to see which code line that accessed this variable and wrote the -1 value. So that's a nice way of understanding where data accesses are happening and why bugs may occur. That's the last thing I'd like to show you about serial wire viewer tracing. I see we only have 5 minutes left, so I should really speed this up. What I also want to show you is that we have kernel-aware debug support. We have that for a number of different RTOSes, FreeRTOS perhaps being the most popular one. So this application is running FreeRTOS, and we can visualize various kernel objects in views such as the task list view, semaphores, queues, etc. I can toggle stack checking by clicking this button to see how much minimum free stack size we have for each task. One cool feature I definitely want to show you, which could help you a lot in your daily development work, is the fault analyzer. The fault analyzer is a tool, a view, which helps you understand what goes wrong when your CPU core hard faults, or you get a bus fault or memory management fault, or any type of fault escalated to hard fault. So let's now again continue the execution of this application. We see that it seems the system is live because we're generating data here. Now I'm going to push the user button on the board. Doing so is going to set the CPU core in a hard fault state, because I've simply written some code that does that. So I click the button and the graph goes dead, as you see. Patient died. So we suspend the execution and we see that we're in a hard fault handler. But where did we actually come from? We only get this information, signal handler called. Well, in order to understand that, we can use the fault analyzer view, which now is populated with some useful information for us. It tells us that it's a bus memory management or usage fault. So what happened? It's one of these. If we dig into the core registers a bit deeper, we can see that it's an attempt to perform a division by 0. So that's what happened, the first question that needs to be answered. Then the question is, where did this happen? And by clicking this button and this button, we can jump to the corresponding C statement line that drove the CPU to hard fault, or the assembly instruction, and or with these buttons. So now we know where it happened. And then we also show the stacked fault exception stack frame, the values of the registers when the CPU crashed. Let's close that down. With all this information, we should be able to tell both what happened, well obviously, where it happened, and with this information, why it happened. So it's a quick way of understanding, better understanding why you get hard faults. I noticed that I have about 1 minute left. That that minute I'd like to just show you something different that also is available. I have connected another board. This is connected using a Sega JLink instead. The JLink supports live variable watch, so to speak, which means that we're able to monitor different variables as they are modified by looking at the data bus. And this is only supported with Sega JLink. So let me see. I have here the live expressions view. I have a counter, a global variable, and I let my application run. And as you see, while the application is running, the counter here is updating with incremental values of the variable. So that's possible with a Sega JLink, but not enabled with an ST-Link, for example, or a CMSysDub. So yeah, I think that's all we're going to be able to cover today. I might just highlight or point out to you some other options that you have. And we have an integrated terminal view, could be useful for you, which enables setting up target communication for serial communication. We also have ETM and ETB tracing. So the tracing we looked at today was serial wire viewer tracing. It's an event-based type of tracing. It's the cheap version, which gets you quite far. It's in the all Cortex M3, M4, and M7, mandatory by design. ETM tracing instead is real instruction tracing. We support that with a Sega JTrace or with any probe if the target has an embedded trace buffer implemented. So just to show you the view, here we show data, we can show function nesting, we can show each C statement where in the whole instruction execution flow that we have recorded. We can show mixed C and assembly, etc., etc. You can export it for offline analysis in a comma-separated value list and search through the buffer, so to speak. You also have the special function registers view that enables you to peek into the special function registers of your microcontroller. So for example, if we again take a look at this example where we're setting up some LEDs, then LED 3 here is GPIO-D pin 13. So if I just start by expanding GPIO-D here, then I step over LED 3. So if I initialize, I could probably assume that some of these registers are going to be modified. Let's look at GPIO-E and D at the same time. And I step over this first statement. It should do something to GPIO-D port 13. Step over. And you see yellow highlighting here because these registers were changed in some way. Now, when I have enabled pin 13 on port GPIO port D, then I can look at the output data register here. So now, by toggling this, I can see that my LED on my board is turning on and off. So if I have a read-write access to the register, then you can toggle different bits using this view also. So if I do like this, you should see that all these bits now are on, all the LEDs has been initialized and turned on. Yeah, I think we'll stop there and see if we have any questions. I'm a little bit, as always, consumed too much time. So I'll hand it over to you, Stephen. Do we have any questions?
Yes, we do. So you were just talking about ETM tracing. Could you spend a little bit more time with that? We have a participant that wanted to see more detail on ETM and maybe ETB tracing.
Okay. Well, I can't demonstrate it without a hardware, a Cortex M3, M4 microcontroller that has the ETM module as part of the core. And don't think my board has that here. What we can say is this. As you've seen, we have this view to visualize data. If we use this representation, you will see function call nesting. So which function called which and how did we return? That's how that is going to be represented to you. So on a function level, we see calls. We can also see all C statements, and all assembly instructions that were executed, and the mix between C and assembly. What you can also do is to, which is of course very important, you don't want to trace the complete execution session of your embedded system necessarily. You want to have triggers to start and stop the trace, and that's also possible. So let's say perhaps I want to start tracing on this line, then I could do, let's see if I can find that. Perhaps I need to be in a debugging context, sorry. Perhaps I even need to have ETM enabled. We'll see. Otherwise I'll just have to describe it. Well, yeah, add trace trigger. Okay, you need to have ETM enabled, but what you can do is to add trace start and stop triggers here. Add trace start, add trace stop, to just capture instructions executed between two different, let's say, parts of your application. You can also set the start trigger to happen when you have an access within a certain region of the memory, and have it stop recording on another region in the memory. So either you start on a certain instruction, program counter value, or on an access to a certain memory region. Those are the two options. If there are, perhaps there are more specific questions, otherwise I'll continue with the next question, if there is such.
Okay, so what's the system overhead of using serial wire viewer?
Yeah, good question. The system overhead depends on which feature in the serial wire viewer you are using. So let's go into the configure trace. And the only feature here that actually generates an overhead is using the Idm ports for a printf type of tracing. But the code could be made very small, just a C macro that writes a byte to a certain port. So we're talking really small overhead. So that's the only thing that actually creates any overhead to the application. The rest is a hardware support that does not have any memory, does not require any instrumentation, and thereby there are no timing penalties using serial wire viewer. I hope that answers the question.
Okay, thank you. I have another one here. Hang on just a moment. So,
sure.
What about using serial wire viewer capability along with kernel-aware debug? Can they be combined?
Sure. I suppose it's a matter of how you wish to use it. I mean, you could monitor some kernel object, provided that it's maximum a word variable with a data watch and trace point. So these comparators. So you could have kernel objects showing live here, but or you could instrument the kernel to output trace messages on the Idm ports. Those are two options, but you cannot get live data in the kernel-aware debug plugin here. For that you need to suspend the target. So if that was the question, then the answer is no. But if my first interpretation was correct, then there are multiple different options.
Okay. Another question. This just came in. Are you using SWD or JTAG with Serial Wire Viewer?
Serial Wire Viewer requires Serial Wire Debug, SWD. So this is the 2-pin interface with let's look here instead. And the Serial Wire Viewer adds a third pin, a trace pin, which transfers data back to the debugger. So yes, SWD interface is necessary. It only works that way.
Okay, we have another questioner that wants to go back to the printf redirect. Mm-hmm. How do you link printf to the port? How do you set it up? And can you configure port 8 to show the printf output?
You can do it in different ways. By default, printf is set up in the CMSIS core libraries actually. So this is this is an enforcement by the ARM CMSIS team to print printf statements to port 0. Let me see if I can find that. So let's take a look at how this happens. Now I'm in the wrong project. That's not very useful. Close project. We go to main. We see here printf. I go into printf. Printf is then implemented here in what we call tiny printf. It's a special atomic implementation that reduces the code size. Eventually printf will call the write function here. If I go to the write function, we end up in yet another atomic source file, atomic supplied source file called the system calls, syscalls.c. Here we have the implementation of the write function. So what I have done, which is special in this project, is that I have added, this code line, at least these code lines, which simply sends each character in the string to the function called itm sendchar. So what is itm sendchar? Well, let's take a look at where this is implemented. It's implemented in core_cm4.h, one of the CMSIS standard files. Let's expand that. You find it in library CMSIS include core_cm4.h. So here you see the implementation, and it's always sent to port 0. You can of course override and change that. No problem. Another interesting thing is that in this implementation you will actually stall the system because you're waiting for the Idm port to transfer the trace data back into the debugger until it continues the execution. So you may want to implement your own version of this. Let's see if we also have something here. 1 second. You could also just write your own C macro that points to the memory mapped addresses where the Idm ports are located. In the memory map for the Cortex M3, M4, M7. I don't know it from the top of my head, but shouldn't be too difficult to find. Does that answer the question?
It appears. We haven't heard any follow-up questions on that topic.
Okay. Mm-hmm.
What if I'm using an I.MX part? Can I do the serial wire viewer with that?
No, you can't. Freescale or NXP IMX is a Cortex A application processor. I doubt they implement serial wire viewer. I think it's only available in Cortex M3, M4 and M7. Cortex M0, or if it's M0 Plus or both, I'm not sure, has another type of tracing. So this is only for M3, M4 and M7.
Are there other questions that we should answer today? Please write them in the question box and we'll try to get to them. Is there anything you wanted to spend more time on, Matthias, while we're waiting for this, for further questions? You rushed through some of it because of the time.
Not, well, nothing I have planned. We can always play around. What I like with an Eclipse-based environment is the capability of doing debugging of two targets at the same time. So let me just close others, open that main and open that main. So if you're doing either multi-core debugging or trying to debug two microcontrollers at the same time, perhaps they're communicating with each other using some interface, then you can, oops, am I already using this? Yes, I was, of course. Sorry. Then I can launch debug sessions for two projects, two different microcontrollers at the same time. That shouldn't be an issue. So now I'm debugging both the F4 discovery board and the 32B eval board at the same time. It can be kind of confusing, so a cool thing you can do here is to actually open multiple registers views, or whatever you're interested in having multiple views on. So I'm going to open a new view here. Let me do like, I'm going to do like this. For people interested in multi-core or multi-processor debugging, this is nice. So what is a problem here is that what context am I actually analyzing? So if I click here, you see that the CPU core registers has these values. They have that here too. If I click here, both change to reflect this core. Now I can take, for example, this register's view and pin it to this debug context, which means this one is now pinned to this board or this ELF file. And then I go here and I take this view and I can pin it to this ELF file or the F4 discovery board instead. So now regardless of where I click, I will always see updated registers of the unique boards in these unique views. So you can spawn twins of these and associate them to different contexts. And that is useful in many different views, such as I think it's available in the memory view, let's say. Also, you can associate that to a certain context as well. Not very relevant for someone not doing multi-core or multi-processor development, but I like having the availability of doing everything in the same workbench or IDE instance. So, are there more questions?
Someone's asked, how would you calculate a time delta between two entries without having to manually do it?
Yeah, that's a good question.
We're using an Idm port to determine elapsed time.
Yeah, I see what you mean. There should be a possibility for that to just perhaps use the trace log and select two different ITM packages and then do a diff of that to see the delta between the times. So what I think the question is saying is, let's see here, let's just take something. We could instrument this application to put out a byte on the ITM line here and then another byte here. Then we would be able, by timestamping this byte and this byte, to see how long time it took to execute this part. So, because we would get a timestamp here and a timestamp there, but what they are searching for is a way to do a simple delta of those timestamps, I believe. And no, there is currently no way to do that in a simple one-click operation, unfortunately. Let's see, are we able to do like this? Oops. What you can do is the format of the serial wire viewer trace log is a comma-separated value list. So you could potentially export, just do a copy-paste into Excel and do offline analysis if you want to automate this. But I think that the question is really to be able to do this quickly on the fly when you're in a debug session. By the way, sorry,
I'd say you're pretty good at answering on the fly.
I've had this question, I believe, before, and I do think we have a feature request for this. It just hasn't been prioritized. So, yeah, that's where we are.
Okay. So it wasn't on the fly. You already knew the answer. That's good.
Yeah, I shouldn't have given that away, should I?
All right. I don't see any more questions. I want to thank everyone for attending today. And we will alert you when new webinars are scheduled. We intend to schedule these on a regular basis going forward. We're alternating between getting started with TrueStudio Lite and some of the advanced features in TrueStudio Pro. So thank you again. We will prepare an archive video of this webinar and send it out to you, send you a link no later than 48 hours from now. And again, thank you for attending. We're going to close the webinar now.